In this video, we learned the CNN components such as input channel, padding, asteroid, and pooling. Input channel. The term channels refer to communication science. In general, a channel is transmitting information using signals. A channel has a certain capacity for transmitting information. But in this context, let's assume that we're talking about 2D convolutions applied on image. In image processing and digital imaging, a pixel or picture element is the smallest controllable element of picture represented on the screen. In some contexts, like camera sensor, pixel refer to single scalar element of multi-component representation, while in the other contexts like medical imaging or MRI, it refers to a set of component intensity for a spatial position. Each pixel is a sample of original image. More samples typically provide more accurate representation. For example, the high resolution images, they have the more pixel and the intensity of each pixel is variable. For example, in gray scale image has a single input channel and value of each pixel is between 0 till 255, where the 0 shows the black and 255 correspond to white color. In color imaging systems, a color is typically represented by three or four component intensity, where, for example, in three channel, we have red, green, and blue, or RGB, or we have also another four component like cyan, magenta, yellow, and black. In RGB, each pixel can be represented by a vector of three numbers, each ranging between the 0 till 255. For example, look at this light pink images. We have the three different values for each channel. For the red, we have 252, for the green 233, and blue is 230. Therefore, with like a combining of these three values, we can have the light pink. Firstly, we will look into the necessity of padding with one example. Suppose we have input size of 5 and 5 and filter size of 2. By moving a filter on the top of input, we will create our feature map. Here the size of feature map is equal to 4 in 4. Indeed, like for an input size of I, filter size of K, we can create the feature map is I minus K plus 1. If the width or height of our kernel is like bigger than 1, we will see that the width and height of the feature mapping output gets smaller. And this occurs due to the fact that feature map slides over the input and computes the element-wise multiplication, but it is too large in order to inspect the edge of input. And as it cannot capture the edge, it won't be able to effectively end at the final position of, for example, of your or of our row, and resulting in a smaller output width or height. Indeed, padding refers to amount of the pixel added to an image when it's being processed by the kernel of CNN. For example, if the padding in a CNN is set to 0, then every pixel value which added is like 0. But we have also other padding like padding of one also, but like a zero padding is a more popular one. With zero padding, the feature map can remain in the same size after each convolution, which means the network can be go like in a deeper or arbitrary deep. In this figure, for example, you can see a padded convolution versus the normal convolution. Like on top, without padding, the width and height of our feature map shrink rapidly to one after only three convolutional layers, which means we are not able to go deeper. However, like as you can see in below, we by applying a zero padding, the feature map can remain in the same size after each convolution. Therefore, we can go deep as we want and discover more features and more information. And next term is asteroid. Asteroid is the step size or the number of pixel shifts over the input matrix. For example, we have the input size of 5 and 5 and filter size of 3. By having a asteroid size of 2, we can create the feature map as a 2 by 2. By having the asteroid size of the 2, it means we move the filter to 2 pixels at a time. And in general, when there is no padding for input size of I, and also kernel size of K and asteroid of S, we can calculate the output feature map similar to this formula. Note in previous example and so far we have only discussed the asteroid of the one, and if you remember we moved the filter to 1 pixel at a time. And more importantly, a stride convolution is equivalent to convolution without a stride followed by downsampling, as you can see here. So far, we have seen how convolutions work, but there is also another operation which I would like to here introduce to you. It's pooling. Often, as we process images, we want to gradually reduce the spatial resolution of our hidden representation, aggregating information so that the higher up we go in network, the larger receptacle which we have. Therefore, each hidden node in this situation is sensitive. Indeed, we want to downsample the feature map, but optimally we wouldn't actually lose any information. Like convolutional layer, pooling operators consist of a fixed shape window that is also solid over the region in the input according to its stride, computing a single output for each location and transferred by a fixed shape of the window, which we call it also pooling window. And also it's important to know, unlike the cross-correlation computation of the input and also kernels in the convolutional layer, the pooling layer consists no operator. There is no kernel here. Instead, like a pooling operator are deterministic. For example, we calculate the average or we calculate the maximum of the element of each windows. As you can see here is the max pooling when we apply a pooling size of the 2 by 2 with the asteroid of the 2. Similar to convolution, we will get a similar output of the feature map 2 by 2. And here our pooling operator is max pooling. Indeed, in selected max pooling window, we get the maximum values and then move it to the feature map. Similarly, by moving a spatial window to the different location, we can get the maximum element of each window and then move it to the final feature map. And like our final feature map has a maximum number of first window, 8 here, 6 for the second, 9 for the third one, and 3 for the last. Max pooling actually brings us two important properties. First of all, dimensionality reduction, as you can see here. And the second thing is spatial invariance. Means if we have like another order here in this, for example, last window, still we can get the 3 even if it happened here, for example. Popular pooling functions are max pooling and also average pooling, but we have different type of pooling, such as fractional pooling, LP norm pooling, softmax pooling, stochastic pooling, and Beller pooling. These are only a few examples. In the case of average pooling, similar to max pooling, we also here do the downsampling the feature map, but here we get and calculate the average information of each window. As you can see here, we can get the average of this window, and which is like 0.75, and then we move it to feature map. Similarly for the second windows and also for the third one. As you can see here, since we get the average of the values that we have in the windows, this operation, I mean average pooling operation is not robust to it. If we added some noise here, then for we also calculated noise also in these values. Therefore, by applying the average pooling in like our input size, we can calculate the like average pooling with the 3.75, 2.5, 4.25, and 1.75 at the end. If you want to compare max pooling and average pooling first of all use all information that we have so far by operating sum. However, max pooling only use the highest value. And more importantly, in max pooling operation, details are removed. Therefore, it's like a more suitable for a sparse information. For example, when we would like to do image classification. And average pooling is suitable for the dense information, like when we apply natural language processing. Here is also one example which compare average pooling and max pooling. Here is our input origin images from like a toy image. By applying a max pooling here, we can see only the white pixels, but by applying average pooling, we can see at least some details. And if we reverse this image, we can see, okay, in max pooling, we will have something similar to this, but in like average pooling, we will get at the end something similar to the right side. Okay, let's put all the components in one thing. In this CNN, we have like a colored images. Therefore, we have three input channel with a size of 4 in 4 and followed by a filter. As we mentioned earlier, for each channel, we have the like a filter, right? Here our filter size is 2 by 2. We have next, after the convolutional layer, we have the ReLU activation function. After that, we have the pooling layer. And at the end, fully connected. And if we pad or input, now the output feature map can be calculated similar to this formula. We have the input size minus kernel size plus 2 times of the padding layer divided to stripe plus 1 at the end. In this case, we do not have any padding, therefore our input size, which is 4 minus 2 times of the 2, which is the filter size, and divided to plus 1. Since we do not have any padding, therefore our output for the feature map is equal to